So that's what we're going to look at now. So we have spotted it was a factorising problem because of that telltale term involving sin x and cos x. And having factorised it, what we normally do is we say, okay, we need the brackets to equal 0. But it's a little bit more complicated because the brackets have got sine and cos in. But what I want is, I want that bracket to equal 0. So I want sine theta minus 4 cos theta to equal 0. That would be one solution. And I also want the second bracket to equal 0. Sine theta plus 2 cos theta equals 0. How on earth do I solve this? It's easy peasy, because I've got an identity that links sine and cos. I'm going to shift the cos to the other side and then divide both sides by cos. And I'm going to shift tan to work out the actual angle. And I need to find all the angles between 0 and 360, so having shift tanned it, I know that tan's nice and easy, I just get solutions every 180 degrees. Now hang on a minute, you might say, didn't you just tell me, at the beginning of this problem, that we often have to use factorising because we're not allowed to divide by sine, not allowed to divide by cos. Well, this is one of the exceptions. It gives us an equation in tan, and the places where cos theta equals 0, tan isn't defined. Remember, the tan curve disappears off. It's not defined at 90 and minus 90 and all the other values where it's not defined. That's the same as the places where cos theta is 0, so I'm allowed to do it there. So go on, shift tan that for me. Get me all the angles between 0 and 360, and then see if you can do the almost identical process with this one to get another set of solutions. We're in degrees, so that's good news, although it's not good news for me because I've just done radians. Shift tan and -2 gives me a negative angle, which obviously isn't valid because it's outside my range of values. But I know that if I add 180 to that with tan, that's always the way, I'll get one that is valid. 3 sig figs unless it says otherwise. And then add 180 again, I can get and squeeze out another solution. So here we had another sine 2 theta problem that led to factorising. And we've seen that quite consistently, haven't we? Sine 2 theta problems leading to factorising. Now, I don't know if this rings a bell at all, because we have actually come across a problem a bit like this before. It was back in the good old days, back when we were all young and happy.
Still young.
In your, yes, you are. It was in your summer mock. So the summer mock we did had this question here in it. Now this isn't a double angle identity question because we've sort of joined this one a step later. So we're not joining this question at this point. We're joining it at this point, but it's still the same thing. So go on. While it's a little bit of a detour because it's not to do with double angles. But see if you can factorise that one. It's just like the previous one. We know we're going to have a sine theta and some cos thetas in both brackets. I've recognised that telltale sine theta cos theta thing. It's 4 of them in this case. See if you can have a go at factorising that one and then solving it. It'll be a bit like the one we've just done. So it's definitely going to have a sine theta and some cos thetas in that bracket. And it's going to have a sine theta and some cos thetas in that bracket. See if you can work out how many cos thetas you need. And see if you can solve it. I'm going to go and fill up my squirty bottle.
Do you have a
I see that.
No.
I don't know if they want to go with
Shit.
something. She's just come out.
Your eyebrows. You want to use it like you've got that. Shit on as well. Just the normal though.
Managed to factorise it, Harry? What have we got?
5 cos.
So +5 cos and -cos. Let's just check that works. So if I grid that out, I'll definitely get my -5 cos squared. I'll get +5 sine theta cos theta -1. Brilliant. Yeah. So now we're just going to do the whole tan thing again to work out the solutions and I kept doing this morning. sort of been a little bit lazy. I've written my, my sort of accurate ... answer once, and then, I'm pretty safe then just rounding the two other answers because, it's fairly obvious what I've done. So you should get 45 and 225 as well.
Oh, is it all one, is it?
Yeah, cos divided by itself is 1. Did you put 0?
Yes.
Yes, that's an easy mistake to make. Now, going from here to here, we're dividing by cos. So we're dividing both sides by cos theta. So cos theta divided by cos theta is 1. Yeah, that's a good mistake to make now, rather than the exam. Now, I've sort of said that the telltale sign that you get this factorisation, and we're drifting a little bit away from the whole double angle thing, but it's still relevant, is, that's all right, is that. But actually, it's not really, is it? It's the whole blooming thing. Because if you didn't have the sine squared and the cos squared, it wouldn't factorise into a double bracket with sine and cos. So actually, it's a bit misleading to say, look for that, although that's a bit of a telltale. However, I don't want you to think that every question that involves a sine x cos x is going to be a factorised. Yes, sorry. So that was an AS question. That was 5 marks. Do you think that's generous or is that tough? It's easy when you know how, but there's a lot of work involved, isn't it? Because even when you get the factorisation, you've still got all the whole shit term thing to do. Yeah, so have a look at this question, which is on the Maths Genie double angle questions, which I'm actually going to be encouraging you to do. It's this question 5. Now that's got a sine x cos x in it, but nothing else. Nothing else.
So that's just where we actually take.
So this isn't a factorised question. We have come across a question like this already, doing double angles. Anyone spot what I'm going to do? So this is one where you go back to sine 2x. In nearly every example, you start with either cos 2x and a sine 2x, or a sine 2x or a tan 2x, and you replace it with the identity from the trig sheet, and with cos you've got to choose which one you use. But we did do an example when we were talking about cos 2x of going back. Cos 2x, sorry, sine 2x is 2 sine x cos x. So what I've got here, 8 sine x cos x, is 4 lots of that. So actually, to solve this equation, I'm going to go, right, 4 sine 2x is equal to 3, and that means that sine 2x is equal to 3/4. And I can shift sign that to get what 2x is equal to. And then when I get all my 2x solutions, I can halve them to get my 1x solutions. Now, x is between 0 and 360, so I'm going to have to go as far as 720, and with sine, that means 2 full cycles. There's probably going to be a lot of solutions. Now, why can't we do this all the time with sine x, sine 2x, or cos 2x? Well, because in the other ones we've done, you've got sine x's and cos x's as well as the 2x. Here it's just the sine 2x So it's a really, really easy one, provided you spot that first straight goal. See if you can finish off that question there. So you're shift signing 3/4, looking at your sine curve for 2 full cycles, and asking how many angles have a sine of 3/4, trying to find all those angles. Those are your 2x solutions, then you're going to halve them to get your x solutions. Now, I'm perhaps being a little bit overcautious by storing my values in the calculator, but it made it a little bit easier. So I got that, which is the first solution, so I stored that in x. I don't know why I chose x rather than a letter, but there we go. And then my next solution is 180 take away that, so I just did 180 take away x, and I stored that answer in A. And the reason I did that initially was that this solution here is 360 degrees more than that. So to work out this one, I just did 360 plus x, and I stored that in B. And then this solution is 360 more than that. It's a full cycle after it, so I just did 360 plus A to get that one. And then I just did x divided by 2, A divided by 2, B divided by 2, and C divided by 2. And it meant I was sure I had the right answers, and those I rounded to 3 significant figures. I'm being overcautious. When you look at mark schemes, it's always more generous than that. But you know, we might as well use these calculators that we've got. Now, I've shot myself in the foot really, because I have encouraged you in OneNote to have a go at those 3 questions at the end of that section in Maths Genius. So if I have we have a quick look at OneNote, and I've also done something I perhaps should have done to start with, and put it in reverse, so that the most recent stuff's at the top. So I've added a link to that Maths Genius. I mean, all this work I'm doing for you, you could find it yourself, really, couldn't you? But no, I'm putting a link in. We've just done 5, so you've only got 4 and 6 to do. So those are really worth doing now. You're in a position to do those now. The stats and mechanics code, that's fairly substantial, isn't it? But I recommend that you tick over with that, and I really hope that you've knocked those 2 off. And if you haven't, please crack on with that. And it would be really nice to have a bit of company after school today. Oh no, actually no, I'm going to get my booster. Sorry, after school tomorrow to help you out with any problems. Yeah, that's that. So that's on that independent revision page. Please, if you haven't got something to do that I perhaps haven't given you something to do in a lesson, that's where you should be turning when you come to sit down and do some independent study. So we have looked at solving equations. We haven't done much proving, and that's because the proof is sort of part of the solving. So I'm sort of rolling it all into one. But we've looked at questions where we are replacing cos 2x, and that nearly always gives us a quadratic. We've looked at questions where we're replacing sine 2x, and that nearly always results in factorising. But we've also just been reminded about examples where you go back to sine 2x. We did a couple of tan 2x examples yesterday. So we've got pretty good coverage of the identities. And examiners clearly feel that, provided you can remember the identities, which of course is not straightforward, but there we go, that's all quite easy. So they obviously scratched their head and said, how can we make this a bit harder? And that's what we're going to look at now. So the next step is still with double angles, but it's when we have replaced x with something else. And I don't mean with theta or y or something, I'll explain why. So we're replacing x with something else. Okay, not a 2x in sight, okay, not a 2x in sight. So, I'm poised, I've sat down in my maths exam, I spent 5 minutes deriving the identities from the formula sheet, because that means I don't have to remember much. And I open the book, and question 1 is this, and I think, no. I can't help notice, though, that this is double this. And that catches my attention. So here's a good thing I could perhaps try doing. What if I replace 3x with something else? I don't know, I'll call it A. So this becomes minus the cos of A. So 6x is going to be 2a. I hope it's the cheap dongle I bought and not my laptop, because that will break my arm. All of a sudden, it's a double identity problem, a double angle identity problem. So go on, replace sine 2a, don't be fooled, but don't be worried by the fact it's a different letter, with the identity we've got. We've only got one for sine 2a, 2 sine a cos a. And as is often the case with these problems, we're going to have to factorise to solve it. See if you can get somewhere with that. You need the solid, use the solid, you use the solid, go back to your list. Why you stood there? Have you used the solid or you used it? Okay, so go to another tool, go to the second. So just that process of replacing 3x with a different letter turns it into a problem that we are sort of familiar with. And I could factorise and pull out a cos a. So what I now can say is, right, for this to be 0, cos a will be 0, or 2 sine a minus 1 has to be 0, so sine a would be a half. And hang on a minute, there's something at the back of my mind which is troubling me. Oh, hang on a minute. A is actually 3x, isn't it? So I'll tell you what, at this point I'm going to put it back in. Cos 3x needs to be 0 and sine 3x needs to be a half. So what we've done here, Grace, is we've taken a problem that doesn't look like a double angle identity problem, but I noted that this was double this. So I replaced that with a, so that was 2, and all of a sudden it's it's quite an easy problem to solve. Now,
I wanted that back.
I can now do shift cos of 0 and shift sine of a half, but I've got 3x, so I've got to make sure I go as far as 540 degrees. So that means, 1.5 full cycles. So for cos, it's going to be 1, like that. For sine, it will be 2. So once you get your 3x solutions, and remember we find all of them first, you then just divide them by 3 to get your x solutions. Remember the good old days when there was one solution, one answer to an equation? This question's got 7. At least they're all quite nice round numbers, and we're working in degrees, so not too bad. And remember, if you have a brainstorm in the exam, you can plot y equals cos 3x and y equals 0 and ask where the two intersect. That will, using the G-solve button, that will get you the same answers. Sort of hoping you don't need to, because these are 19. So I get 150 for that one, and then this is 30 degrees after 360, so that's 390. So my x solutions are 30, 90, 150, 10, 50, and 130. And that was made, okay, I'll use the word easy, advisory. It was made easier by spotting that with the variables in this equation, 3x and 6x, one was twice the other. So I replaced the smaller one with a different letter, which meant the bigger one was 2 times that letter, and therefore I could use the identity.
No, another one.
Sorry?
Another one for sign.
Oh, there is. Sorry, yes. Well, thank you for pointing it out. So I've got 540 minus 30, 510. Thank you, which is 170. Thanks, Matt. Okay, so let's look at a new example of this same thing. So we're asked to solve 4 sine x equals sine. Okay, so again, I can't help noticing that this is twice this. So James, what am I going to replace with A? In the last one I had 6x and 3x, and it was the 3x I replaced.
So x over 2.
Yeah, the x over 2, the smaller of the two variables, that's right, yeah. And that means that that's going to be 2a.
It's always the smaller of the two variables.
That's correct, yeah. Because that means you get an A and a 2A, or whatever letter you choose to use. So I've got 4 sine 2A equals sine A. I'm going to replace that, and sine 2A, we punch the air when we get a sine 2A question, because there's only one identity with sine 2A in it. That's going to be 2 sine A cos A. No choice like we have with cos 2A. I'm going to take the sine A away from both sides, and as is so often the case with sine, I am going to factorise to find my solutions. So I guess there's probably going to be intermediate step there. So sine 2A is 2 sine A cos A. So 4 lots of sine 2A. Hopefully you can work out what that's going to be. fight the urge that you feel to divide by sine. That would still give you one of the right solutions, but you'd lose the sine A equals 0 solution. Instead, get it all on one side and factorise. Then you've got two solutions, and the good news is that if x is between 0 and 360, x over 2, we only need to look as far as 180, which is great news. Much, much, much easier. So we're looking for three solutions. Okie dokie. So it doesn't matter when you replace your A with x over 2, and of course you don't actually need to replace A with x over 2 if you don't want, if you do x over 2 with A, you know, if you can spot it and you're confident enough. I mean, that's just too much for me. I need to do the substitution to get it clear in my head, but there we go. So those are the solutions that we get. So let's go back to my favourite question of all, which is on page 180, question 5. And there are two of these on there. They are D and E. A little bit different, but there we go. I don't know if anyone finds that a bit hard to see in the book. So I've replaced 2 theta with a, so it becomes that.
Okay.
I then use my identity for sine 2a, 2 sine a cos a. I moved everything onto the one side and factorised, so got that cos a would have to be 0, or rather cos 2 theta would have to be 0, and sine a would have to be a half to make that bracket 0, so sine 2 theta is a half. The range of values for theta is with 0 to pi, that's 180 degrees, so 2 pi needs to be 0 to 2 pi. 2 theta, sorry, needs to be 0 to 2 pi. So here we go, that's one full cycle. So that's nice and easy. That's pi, that's 2 pi, so it's pi over 2, and that's 1.5 pi, so that's 3 pi over 2, and half that to get pi over 4, and 3 pi over 4, so those are the solutions I get there. Here, it's 30 degrees, isn't it, which is pi over 6. So that's my first solution, pi over 6. So this is 1/6 of a pi before a full pi, so that's 5 pi over 6. And so that's theta will be half of that, pi over 12, and 5 pi over 12. I think I've done that a bit quickly. Let's just double check. Yeah, we're okay. Oh, hang on. Yes, sorry, yes, they just written different. So I guess that sets us up nicely for you to do E before next lesson. So do you want to make a note of it? It's page 180, question 5E. So some of you will have already gone to it, I'm sure. But yeah, if you have a go at that before next lesson, we will start next lesson by going through that one.